So transportation problem, which we already saw, it was about, do you remember this? We had three companies, three stations, and we wanted these companies were supposed to take passengers from one station to a Pasadena convention center. And we didn't know how many each company should take. Each station had a demand, 35, 10, 10. Each company had a capacity, 30, 24. And then there was a cost involved for taking one passenger from station 1 to the convention center by company A. Company B's cost and C cost would be different. So for that, if you remember, we modeled it by saying Xij is the number of people taken from a station I by company J. In this case, I was 1, 2, 3. Company was J was ABC or 1, 2, 3 also. Objective function was just minimize 15 x11 plus 13 x12. Basically, multiply each cost by the number of people that company takes. This would be our variables. And then we had two sets of constraints. Demand constraints, making sure that all the people, making sure that the people these three companies take from station 1 is greater than or equal to 35, because there is a 35 people demand there. Same thing for a station 2 and 3. And also we had a set of constraints and capacity, which was what is it? Making sure that the total number of people each company takes is less than or equal to. The demand was greater than or equal to. Capacity is less than or equal to the total they can take. All right, so that was the problem. And then we have a lot of problems that are similar to that. For example, let's look at one. Power co. There is a power company that has 3 power plants, plant 1, plant 2, plant 3. And then there are 4 cities, city 1, city 2, 3, and 4. Each city has a demand, million kilowatt hours, 45, 20, 30, 30. And then each plant has a capacity for a supply, just 35 million kilowatt hours, 50, and 40. So we don't know how much of the demand of each city each plant should satisfy. So that's a problem. But this is very similar if you think about it. It's very similar to the problem we just saw, which is there were 3 companies, 3 stations. We didn't know how much of the demand of each station each company should take or fulfill. This is exactly the same. If you were to model this problem, minimize the cost meeting each city's peak power demand. Xij would be number of million kilowatt hours produced at plant I sent to city J. And with that, this would be our model, which is minimize 8 times x11, 6 times x12, and so forth. This is very similar to what we had. And then we would have, again, 2 sets of constraints. One for the plants or the supply points, making sure that x11, x12, x13, x14, the amount that goes to city 1, 2, 3, and 4 from plant 1 is less than or equal to the amount that plant 1 can supply. And for the cities, because it's a demand, it's not supply, that's to be greater than or equal to, which is total amount that comes from plant 1, 2, and 3 should be greater than or equal to the demand of city 1, which is 45. The same thing for city 2, 3, and 4. And Xij's in this case were just positive. So this is also a transportation problem. In any problem that you see a similar structure, you would call it a transportation problem. Although here we're transporting a power. And then you can show it with this on this graph. where the nodes on the left are the suppliers, the nodes on the right are the demand points or the cities, and DJ shows the demand of each city, SI shows the supply amount of each power plant, and these edges or these arcs that connect plants to cities basically show the values, basically show the variables, decision variables. You see that x11 is 0, x12, so this is just a graphical representation of a solution for this problem. In this solution, x11 is 0, x12 is 10, x13 is 25. Let's check. Sum of these two is 35, and then x14 is 0. So total amount supplied by plant 1 is 35, and it is less than or equal to the amount that it can supply, so that one checks. For plant number 2, the total is 45 plus 5, 50. That one is also not exceeding the amount it can supply. Same thing for plant 3. Some of these is 40, not exceeding the amount it can supply. And same thing for the cities. Total coming to city 1 is 0, 45. So it is more than it needs, which checks that constraint. Actually, the demand is 45 for city 1. So it exactly supply receives that much, not more. Same thing for city 2, 3, and 4. For example, city 4 is 30 plus 0 plus 0. So 30, and its demand was 30. So this is a feasible solution, and it turns out to be the optimal solution. Z star, which is the money, is $1,020 for this for this solution. So this is just a different example, but same structure, same pattern. Whenever we are facing problems like that, we call them transportation models, transportation problems. And to model them, we always have a set of M supply points, company ABC or power plant 1, 2, 3, and supply point I can supply at most S sub I units. So S sub I is the total amount supplier I can supply. In the problem of PowerCo, we just saw M was 3 and S1 was 35 and so forth. And then we have a set of N demand points to which the good is shipped. Demand point J must receive at least D sub J units. In this example, we just saw N was 4 because we had 4 demand points. Note that M and N are not exactly necessarily the same. Demand of point 1, node 1 was 45 and so forth. Each unit produced at supply point I and shipped to demand point J incurs a variable cost of Cij. ThoseCijs were given in that table, 8, 6, and so forth. As you see, C12, 1, 2 was $6. So with that, the transportation model is going to look like that. And this is, you can read this now better with the examples that we just solved or modeled or formulated. You should have an easier time reading this. This is the generic or generalization of the transportation model that works for any problem that has a number of suppliers, a number of demand points, where Xij is number of units shipped from plant point I to demand point J. We had a table of cost. That's why here we have two summations. We have two indices, X, I, and J. And then here you see for each supplier, we want to ensure that total amount supplied is less than or equal to amount it can supply. For demand points, total amount supplied is greater than or equal to the amount needed. Okay. And that's a generic model. So we know how to model transportation problems now. Then the question is, how do we solve them? So when we're dealing with a specific type of problem, a class of problem, usually there are many different methods or algorithms developed to solve them, which is a good thing because you may see a problem in industry and you see that it's similar to the transportation problem or the TSP problem or the set covering problem. And then you just go and customize the solution methods that are already developed for this. You don't need to come up with a new algorithm to solve it. So today we're going to look at a few heuristic methods that find a feasible or a starting point, basic feasible solution for the transportation problem. To do that, first we need to set up what we call a transportation tableau. In a transportation tableau, we have m times n cells, which is m rows, n cell, n columns, and yeah, and then in the corner of each cell, we also add the cost of shipping one good, one unit from supplier I to demand point J. And at the end, at the bottom, we also add the demands and the supplies on the right. And then we utilize this table in three different algorithms that we'll use to solve it. For example, for the power core problem, this was these little cells were the costs given in that original table, and the values you see here are the decision variables. And these are the demands, supplies. Plant 1 is going to send 10 units to city 2, 25 units to city 3, and so forth. That's what the transportation tableau is. Next, one thing that you may notice here, what is the sum of or total demand here? Total demand, 30 plus 30 plus 20, that's 80, plus 45, 125. What's the total supply? 90 plus 35, 125. So demand and supply are the same. In that case, we would say the problem is balanced. In that case, we would say the problem is balanced, but that's not always the case. Sometimes demand is greater than supply. If that's the case, there is no way you can satisfy all the demand. And we would say the problem is infeasible. But if demand is less than supply, which means you have some supply that will go unused, in that case, you can balance the problem by adding a dummy demand point, with a cost of 0 that can take all the unused resources, unused supplies. So if supply is less than demand, infeasible. If it's greater than, add a dummy point. For example, let's say our supply was more than our demand. Just look at the demand here. 4 plus 20 plus 30, that's 90 plus 30 is 120. Supply 125. So we have 5 excess supply. So you add a new demand point, dummy CD5, which doesn't exist, that has a demand of 5. What's that 5? It's the excess total supply that we have compared to total demand. Total demand, total supply 125, 120. The difference goes to this, the demand of this dummy point, dummy city, dummy node. Yeah. So solution methods or heuristics for the transportation problem. There are three solution methods. One is called the northwest corner minimum cost Vogel's method. These solution Vogel performs better than the first two, but the first two give you at least a feasible solution. And before you start using any of these, you want to make sure that the problem is balanced. Let's look at the northwest corner method. Why are we doing this? Because nowadays computers solve all of these problems, but we want to get used to seeing how algorithms work, how iterations work. We already saw that in simplex method. Now the simplex method, if you remember, was generic, which it didn't care what the actual problem was trying to solve. It saw the problem as a bunch of matrices, C, A, B, right? A C matrix of coefficients, X matrix of variables, A matrix of coefficients and constraints, and B matrix of right-hand side values, or the vector of right-hand side values. It didn't really know what was going on. But in this case, this algorithm, northwest corner method, it knows that you have a bunch of supplies, you have a bunch of demand. It knows that. It knows that it's not just a bunch of matrices. And it also needs this problem to be balanced. So, and in this case, it doesn't really care about cost because it just wants to give you a feasible solution. First, balance the problem. Next, find the most northwest cell, which is, in this case, when we start, is this point here, this corner. Is this one. Add minimum DJSJ, which means if this is my selected cell, what's the minimum of 2 and 5? Is 2. It says add that here. Add 2 here and then deduct it from this and that. So this becomes 0, this becomes 3. Subtract that minimum value, minimum of 2 and 5, from both these 2 points, and cross the row column whose demand or supply is 0. If I deduct 2 from these 2, this becomes 0, and then I can remove this entire and cross this entire column because its demand is 0. Now my tableau has reduced to this part. And this value has changed to 3 because 5 minus 2. Are all demands satisfied? No, 4, 2, and 1 are still there. Then go to step 2. Find the most northwest cell here, which is this guy here. Find the minimum of 4 and 3, because it used to be 5 minus 2, it became 3. Minimum of those is 3, add it here. This becomes 0, cross that. Then your tableau reduces to this part. And then now looking at here, 3 minus 4 is 1, by the way. Minimum of these 2 is 1, add it here. These 2 become 0, you cross both, your tableau becomes that. And out of 2 and 3, you go with 2 because it's minimum, you add it here, cross it here. You delete this row, eventually your tableau becomes just that one cell. This is 1, and you add it here. And the values you wrote inside the table will be the solutions, the solution method. Let's solve that problem here. Unfortunately, I couldn't connect my iPad, so I'm not really sure how to do this, but I'll do my best. So step 1, choose the most northwest cell, which is here. Pick the minimum of these 2. Minimum of 2 and 5 is 2. Is 2. 2 minus 2, 0. 5 minus 2, 3. Cross the row column, that's 0. Only this column is 0, so cross that. Now your tableau is here. Find the most northwest cell, which is here. Oops. Let me do it here. Maybe it works better. So minimum of those two is 2. And then if I subtract those two, this becomes 0, this becomes 3. Let me see. This becomes 3, this becomes 0. Then get rid of that entire column. All right, now here the most northwest is this one. Between 4 and 3, I go by 3. And 3 minus 3 becomes 0. 4 minus 3 becomes 1. Which row or column is 0? This one. So cross it. If I cross those, my tableau is only these 6 cells now. The most northwest cell is this one. Minimum of 1 and 1 is 1. So move it here. Deduct it from both. It's going to give you, this one becomes 0. This one also becomes 0. You need to cross both because those are both 0. Now your tableau is reduced to only these 2 cells. Minimum of 2 and 3 is 2. Move it here. Deduct 2 from 2, you get 0. Deduct 2 from 3, you get 1. Which row or cell is 0? This one. Remove it. And then your tableau is reduced to only this cell. 1 and 1. Minimum of the 2 is 1 over here. Both become 0. Done. It's finished. So the values you see here is basically the solution. It means from company A, send or power plant A, 1, send 2 units to customer or demand point 1, 3 units to demand point 2. From supplier 2, send 1 unit to demand point 2. From supplier 3, send 2 units to demand point 3 and 1 unit to demand point 4. So that's basically the answer. Any question about this? That was called the northwest method. Northwest corner method. And then the second method is called the minimum cost method. Very similar to what we had, with only one difference. Balance the problem. Find the cell with minimum cost. So instead of finding the most northwest cell and starting with that, you always start with whatever cell that has the minimum cost. And then you do the same operations. Add the minimum, find the minimum of the row and column of that cell, deduct it from that cell, subtract it, and then whichever is zero, cross it and do that until all cells are covered. Let's look at this example. So in this example, what is the minimum cell here? Minimum cost cell. These are the costs in this corner. What's the minimum value? 2, 3, 5, 6. So this one here is the minimum cost, isn't it? So I select that. What is the minimum of 8 and 10? It's 8. 8 minus 8 is 0. 10 minus 8 is 2. Which row or column is 0? That one. So cross it. Now the tableau doesn't have this row. Out of the remaining cells, which one has the minimum cost? 2, 2. Let me see if I can. So that row is removed. That column, sorry. So from the remaining 3 columns, which one has the minimum cost? These 2. Just pick one randomly. Let's pick that one. What's the minimum of 12 and 5? 5. 12 minus 5 is 7. And then 5 minus 5 is 0. The column or cell that has 0 is that one. Remove it. So the tableau is now reduced to these 6 cells here. What's the minimum cost? 2 again. What's the minimum of 7 and 2? Is 2. Two minus 2, 0. 7 minus 2, 5. Which one is 0? That one. Cross it. So the tableau is reduced to only these 3 cells. What is the minimum cost? 3. So what's the minimum of 5 and 15? It's 5. Add 5 here. 5 minus 5 is 0. 15 minus 5 is 10. All right, this one, 5 minus 5 is 0. So out of these, this column needs to be removed because it has a 0. Now we are left with these 2 cells. Minimum cost 4. Minimum of 4 and 15, 4. So at that here, 4. 4 minus 4 is 0. 10 minus 4 is 6. This is 0, I have to cross it. Now this last cell, minimum of 6 and 6, 6. So problem solved. All supply and demand. Problem solved. So here you're seeing iterations. Every time I see that there are still more cells left, I go back and I follow these steps. Find the minimum cell, find the minimum values in the respective column and row, add it to the cell, subtract it from the demand and supply, then cross that row or column that has 0, then ask yourself, are all demands satisfied? No, go back. So that's one iteration. So I could have shown this in like how many iterations did it actually take? 1, 2, 3, 4, 5. The number of cells that I started working on. 5 iterations. Also, I made a mistake. I didn't do one crucial step before doing these, which was making sure that the problem is balanced. I should have done that in the beginning. Some of the supply is 30, some of the demand is 20, 30. So I was lucky, but I didn't check. Also here, some of the supply was 2, 6, 8, 9, and some of the demand was 9, some of the supply was also 9. So here, how many iterations did we have? Again, 5 iterations. What is the objective function value here?
Cost.
The objective function value, if I ask you what's the objective function value here, you should say the solution is given to you. The solution is, in fact, these values that I've written here. How many goods are sent from supplier 1 to demand point 2? 0. How many to demand point 1? 5. So x11 is basically 5, x12 is 0, x13 is 0, and so on. So your objective function value, or z, in fact, is 5 times 2 plus 2 times 2 plus 5 times 3 plus 4 times 4 plus 6 times 6. Whatever that value that is. That's the objective function value. Is it optimal? Not necessarily, because this method is only ensuring that you are finding a feasible solution. Which one of these methods do you think produces a better result? Northwest or minimum cost? Minimum cost, why? Because it takes into account the cost of, it takes into account the data provided. So it starts with the cheapest route, so it has a better logic. Next method is the Vogel's, which is more sophisticated, but not that different. Balance the problem, same as before. Calculate a penalty for all rows and columns. So what is that penalty? Second lowest cost minus the lowest cost. For every column and for every row, you calculate that penalty, which is the second lowest cost minus the lowest cost. Then you start solving. Choose the minimum cost cell from the row column with largest penalty. So you select the row and column that has the largest penalty, then you select the minimum cost. This has, the reason it does that is similar to the simplex, where in simplex we would go with the most negative cell on the 0, the last row. Subtract that value, this is the same as before, cross the row or column, whose demand or supply is 0. Are you done with satisfying all demand? No, go back. Again, calculate the penalty and so forth. For example, let's say we have 2 suppliers, 3 demand paths. Some of the supply is 25. Some of the demand is also 25. So first I calculate a penalty for each row. The lowest cost 6, second lowest cost 7. The difference 1. That's the penalty. Second row. Lowest cost 15. Second 78. 78 minus 15, 63. Then 8 and 78. difference is 7. 80 and 70, 73, 15 and 6, difference is 9. Which column or row has the highest penalty? This column. So you start with that. Which one has a minimum cost? 7. So that's your starting point. Add the minimum of 5 and 10 there. 5 and 10. The minimum is 5. Deduct it from these guys. So this becomes 5. That becomes 0. Delete the column that has so this became 0. I can get rid of it. Now I have 2 columns left. What is the penalty now? This is the second try. The penalty is 6 minus 8 minus 6, second lowest minus the lowest. That is 8 minus 6 equals 2. And here 78 minus 15 again, it's going to be 63. The penalty here also hasn't changed. So only the penalty for that row changed. So which column or row has the highest penalty out of all of these? It's 7. In this column, which one has the lowest cost? That guy. So 8. What's the minimum of 5 and 5? It's 5. So move it here. If you do that, this becomes 0. This also becomes 0. Now delete the column and row that have 0. So I need to get rid of this column and that row. This column and this row. All right, I'm left with just one cell, which is 15 and 15. So just move that value there. Problem solved. So this method, as you see, is more complex. It does more calculation, but it improved the previous methods, which is it looks more into the data and takes as one more step in each iteration to make sure that the better solutions basically are selected. So the objective function value in this case would be so how many iterations? 3 iterations. 3 iterations is equals 5 times 7 plus 15 times 15 plus 5 times 8. Whatever that is. Is it optimal? No, but it has improved. Interestingly enough, the assignment problem that we saw earlier, it's a special case of the what is it? The transportation problem. What is it? What's so special about it? Here you saw that we had 4 Uber drivers, 4 passengers, and the distance between them is also given. What we're trying to do, we're trying to find the optimal allocation. Which passenger should go with which driver? How do you think this is similar to the transportation problem? What do you think? We also modeled it like that. We had one set of constraints for passengers, one set of constraints for suppliers. How do you think this is similar to transportation problem? Anyone? It is a transportation problem essentially, except the demand of each demand point is just one. Each passenger needs just one, right? And the supply of the supply points is also one. Also, the number of demand points and number of supply points are the same. M equals N. So if that was the transportation problem, assignment problem is a subset of that, where M, number of supply points, is the same as number of demand points. And for the assignment problem, in general, we have N, 5, which means we have one set with 5 items, another set with 5 items. We just need to decide who goes with whom. It's like a matching problem. Xi J, 1 if driver takes passenger J. What was it for transportation? Xi J was not just 0 or 1. It would be, for transportation, it would be a positive value, including 0 and 1. But it could be the number of units, 2.5, 30, 5,000, whatever. Objective function is the same. Constraints have changed. For transportation, sum of Xij for all I would be less than or equal to Si. Here it's equals 1. For demand, it would be greater than or equal to Dj. Here is equals 1. One example of that is this problem, where you have 4 machines and 4 jobs, and each job has a different setup time on the machines. And you want to assign these jobs to these machines in a way that total setup time is minimized. This may be relevant to what you do at work. You have 4 machines, 4 jobs. Each job has a different setup time on the machines. You want to know who should go with whom. This becomes especially challenging when the number of machines and number of jobs is larger. For example, 20 machines, 20 jobs. In that case, it's not that easy. So the problem here is, how do we do this assignment, this matching, so that total setup time is minimized? If we model it again, very similar to what we had, making sure that each machine takes 1 job, each job is assigned to exactly 1 machine. And if you solve it, you'll find optimal assignment. Just like the transportation, we also have heuristic methods for the assignment problem, but I'm going to keep that for later. I think it's enough that we looked at the transportation problems. With those, you should be able to do the next assignment. But I'm going to pause here to answer any questions you may have, and also work with those of you who are here, including Rashid, on their project to see what you have, and if you want to talk about your project, that would be a better use of our time at this point. So anyone from online students, have you worked on anything you want to talk about? Or do you have a model that you want to show to me? Please let me know. That's the case. I'm going to pause the recording here.